Here we are trying to understand the relationship between rate expression and reaction mechanism. And here is our reaction: nitrogen 2 oxide combining with hydrogen gas to produce molecular nitrogen and water vapor. And based on experimental data, and this is the rate expression that was deduced from the experimental data. So reaction rate equals to, or initial rate equals to, rate constant times the concentration of H2 times the concentration of nitrogen 2 oxide. Now from this rate expression we can see this reaction is first order with respect to hydrogen and second order with respect to nitrogen 2 oxide. And this was the suggested mechanism. So the mechanism that was suggested by chemists was this. So in the first step, hydrogen combines with nitrogen 2 oxide, forms X, which is an intermediate. So that step was found to be fast. So when you say fast step, basically we are saying that this step has low activation energy. The energy barrier is pretty low. And in the second step, the X, which is an intermediate, combines with nitrogen 2 oxide again to form another intermediate Y plus H2O. And they found out that this step was found to be slow. Now what does that mean? It has high activation energy. That's what a slow step means. And in the final step, this intermediate Y combines with hydrogen to form, or to give, N2 plus H2O. And this step was also found to be fast, which means the activation energy is low. Now our goal is to understand if this reaction mechanism is consistent with our rate expression. That's our goal. So let's find out. And to do so, well, before that, let me clarify what X and Y are intermediates. Now what does that mean? Well, intermediates are basically molecules or ions that are formed. They're simply consumed during the course of the reaction. That means they might be produced in one step and they might be produced in the next step. So you don't see the intermediate as final product. So they're simply consumed during the course of the reaction. Okay, so let's go ahead and try to understand if this reaction mechanism is consistent with our rate expression. And to do so, the rate of overall expression, or the rate of overall reaction, so the rate of the overall reaction should be equal to rate of the slowest step. Rate of the slowest step. And the slowest step is also known as the rate determining step, RDS, rate determining step. So that is the rule. The rate of the overall reaction, this rate, should be equal to the rate of the slowest step. So based on our rate expression, the overall rate equals to rate constant times the concentration of H2 times the concentration of NO. This should be equal to the rate of the slowest step. So let's see what are the two reactants involved in the slowest step. So that is, we have X, the intermediate, and NO in the slowest step. So I'm getting these two concentrations from here. Those are the two reactants involved in the slowest step. But if you look carefully, X is basically an intermediate formed from H2 and NO. So I can rewrite the concentration of X in as concentration of H2 times concentration of NO. So this can be written as H2 concentration times concentration of NO times NO. So basically this is the concentration of X. That's what it means here, right? So this is nothing but the concentration of X. So if I carefully rewrite the final step, that I can say that this is equal to H2 concentration times, so I have concentration of NO multiplied by concentration of NO, so I can write that as concentration of NO whole squared. And let's see what we got on the left hand side, which is our initial rate expression. This is the rate expression that we had from the beginning. Rate constant times concentration of H2 concentration of times concentration of nitrogen 2 oxide whole squared. So we can say that that rate is basically consistent, or in other words I can say that our rate expression is consistent with the slowest step of our reaction mechanism. So they're consistent. And just to, before we conclude this video, I just want to talk about another term, vocabulary, which is molecularity. What does molecularity mean here? So when you say molecularity, we are talking about the number of molecules that are involved in the slowest step. So if I base it on this expression, I can say altogether in the slowest step we have 2 molecules of NO and 1 molecule of H2. So the total number of molecules in the slowest step is 3. So we can call that as termolecular, which means there are 3 molecules involved in the slowest step. 3 molecules in the slowest step. So that's another important vocabulary term. So whenever you talk about molecularity, simply count the total number of molecules in the slowest step. So here basically I can say there are 2 plus 1, 3 molecules involved in the slowest step. So it's a termolecular reaction. So the rate expression is consistent with the reaction mechanism and the molecularity is 3.